Today we are going to talk about straight lines. In Euclidean geometry, we assume that all geometrical objects are made of points. Just like our body is made of atoms, all geometrical objects are assumed to be made of points. What is a point? A point is a geometrical object which has no length, no width or height. It is simply a location in space. Okay, so we assume all geometrical objects are made of points. Now, a line is a geometrical object which has only length. It has only a single dimension, that is length. So now we know that a line is also comprised of points, right? Now you can perceive a line like this. These are all points, an infinite number of points coming together to form this structure of single dimension, okay, called a line. This would look like this. We draw it like this, right? This is a line. Now at each extremity of a line there is a point. Okay, there is a point. At each extremity of any given line there is a point. Now what is a straight line? If all the points of that line lie evenly between the extremity points, we call such a line a straight line. Okay, here you can see, unlike in this case, all the points of this line lie evenly between the 2 points. These are the 2 points at each extremity. They lie evenly between the 2 extremities. We call such a line a straight line. A straight line. This is how we must perceive the concept of a straight line when we do geometry. When we do plane geometry, we use standard symbols and abbreviations to represent various plane geometrical objects. So how are we going to depict a straight line? Let us assume that we want to depict a straight line called straight line AB. We write it like this. We write it like this. This means that AB is a straight line. This tells us that the straight line has 2 internal points called point A and point B, and that the straight line extends to the right of B indefinitely and to the left of A indefinitely. That is what this means. By consensus, we assume a straight line to be of infinite length. So the straight line must extend to the right of B indefinitely and to the left of A indefinitely. That is what this means. Now, what if we cut a section of finite length from this straight line? We'll say these points of this section is P and Q. Okay, then we call such a finite section of a straight line a straight line segment. A straight line segment, or simply a line segment. Usually when we do geometry, when we say AB is a line, what we really mean is that AB is a straight line. Okay, so when we say AB is a line segment, it means that AB is of finite length and it is a straight line segment. A straight line segment is of finite length. So when we want to represent that, let's say the straight line segment is PQ, we write it like this, PQ. We do not have a bidirectional arrow over P and Q. This means that P and Q are the 2 extremity points of this line segment. right? This is how we depict a straight line segment. When you see this, you know that this is a straight line and it is of infinite length. When you see this, you know that we are talking about a straight line segment that is of finite length. Now let us see how we are going to depict a given angle. Now assume that these two lines are intersecting each other at point O. This line is line AB, okay, and this line is line CD. They intersect each other at point O. So point O is an internal point of both CD and AB. It is common to both AB and CD. So AB and CD intersect each other at point O. As a result, you can see that four different angles are formed. This is one angle, this is another angle, from here to here there is another angle, and from here to here there is another angle. We'll call this angle 1, this is angle 2, this angle 3, and this angle 4. So how are we going to depict these four angles when we do geometry? This is how we represent angle 1. We use this symbol which means an angle. Okay, this is angle COB. COB. You can also call this angle BOC. It doesn't matter, right? BOC. BOC is the same thing as COB. Okay, so this is how we represent this angle. What about angle number 2? Angle number 2. AOC or COA. Angle AOC or angle COA. Okay, this is how we depict this angle, angle number 2. AOC or COA. Okay, now number 3, angle number 3. It is angle AOD or DOA. Angle AOD, and also you can call it angle DOA, right? DOA. Okay, this is angle DOB or BOD, angle DOB or angle BOD, right? It doesn't matter if you call it DOB or BOD. Okay, so this is how we depict an angle when we do plane geometry. Now let us look at the very first theorem of plane geometry. So this is the very first theorem of plane geometry. The sum of adjacent angles formed as a result of one straight line meeting the internal point of another straight line is 180 degrees. What is this theorem talking about? Now look at this instance. Let us assume that AB is a straight line and CB is another straight line. So CB meets AB at point B, but B is an extremity point of AB, right? B is an extremity point of AB. So as a result, there is only one angle that is being formed. But consider this case. Let us assume this is AB and this is another straight line CD. So D here is an internal point of AB. As a result, two adjacent angles are formed. What are these adjacent angles? Angle BDC, angle BDC, and angle ADC, angle ADC. Okay, angle BDC and angle ADC. These are called adjacent angles, angles which are adjacent to each other. Okay, so what this, so the theorem is not talking about this instance, it's talking about this instance. It says the sum of adjacent angles formed as a result of one straight line meeting the internal point of another straight line is 180 degrees. The theorem is saying that the sum of angle ADC and angle BDC is 180 degrees. Now we are going to prove this. So we will assume that this is a straight line segment, which we will call straight line segment AB. Okay, and CD meets AB at D. So D is an internal point of AB. It's an extremity point of CD. Okay, so as a result there are two angles. Okay, angle CDB and angle ADC. The theorem says the sum of CDB and ADC is 180 degrees. Okay, the theorem says the sum of ADC and CDB is 180 degrees. Okay, so how are we going to prove this? Now, can anybody prevent us constructing a perpendicular line to AB at D drawn from some external point? Can anybody prevent us doing that? No. We can draw a straight line which is a perpendicular line to AB from, let's say, some point E. So ED meets AB at D and ADE is 90 degrees and BDE is also 90 degrees. So this ED is a perpendicular line to AB which meets AB at D. Okay, that is our construction. So now we know, because of our construction, this is 90 degrees. This is 90 degrees. Okay. Now let us assume that the magnitude of angle CDB is alpha degrees. We'll call the magnitude of this is alpha degrees. Okay, or we'll simply say alpha. Okay, so angle CDB is alpha degrees. CDB is alpha degrees. Okay, now we already know that angle BDE is 90 degrees. Why? Because ED is a perpendicular to AB. So angle BDE or EDB is 90 degrees. Because this entire thing is 90 degrees, this entire thing is 90 degrees and this is alpha, this angle between the lines CD and ED is 90 degrees minus alpha. So what is this angle? Angle CDE. Angle CDE is 90 degrees minus alpha. Okay, again I repeat, because angle BDE is 90 degrees and angle CDB is alpha, angle CDE must be 90 degrees minus alpha. Okay, now what is angle ADC? Angle ADC is 90 degrees plus this angle. angle CDE, 90 degrees minus alpha, which is equal to 180 degrees minus alpha. Okay, angle ADC is 180 degrees minus alpha. Now what is the sum of ADC and CDB? Therefore, the sum of ADC and CDB is going to be 180 degrees minus alpha plus alpha, which is 180 degrees. We have already proven the theorem. Okay, so this is how you prove this theorem. Now I want you to carefully go through this proof. Now let us look at the second theorem. When two straight lines intersect each other, the resulting vertical opposite angles are equal. When two straight lines intersect each other, the resulting vertical opposite angles are equal. Now assume that these two lines intersect each other at point O. We'll call this line AB and this is line CD. AB and CD intersect each other at point O. So as a result, four angles are being formed. Okay, we'll call this angle 1, this one angle 2, this one angle 3 and this one angle 4. Okay, angle 1 and 2, they are adjacent angles. Angle 1 and 2, they are adjacent angles. Why? O is an internal point of AB and DO meets AB. Okay, so 1 and 2 are adjacent angles. From the first theorem, the sum of 1 and 2 is 180 degrees. Similarly, 2 and 3 are also adjacent angles. So the sum of 2 and 3 is also 180 degrees. 3 and 4, they are also adjacent angles. Why? O is an internal point of AB and CO meets AB. So the sum of 3 and 4 is also 180 degrees. Okay. What about sum of 4 and 1? That is also 180 degrees. Why? O is an internal point of CD and BO meets CD. So from the first theorem, from theorem 1, we come to this conclusion. Now the vertical opposite angles are the angles which are directly opposite to each other. These are adjacent angles. 1 and 3 are opposite angles and 2 and 4 are also angles which are opposite to each other. So when two lines intersect each other, two pairs of opposite angles are formed. 2 is opposite to 4 and 1 is opposite to 3. The theorem says we have to prove that 1 is equal to 3 and 2 is equal to 4. How are we going to come to this conclusion from this? Let us see how we do this. Okay, we'll assume that angle 1 is alpha degrees. Okay, we'll use some other color. Okay, let us say that angle 1 is, the magnitude of angle 1 is alpha degrees and the magnitude of angle 2 is beta degrees, magnitude of angle 3 is gamma degrees. These are actually Greek letters, you know, but you can use any letter or any symbol. which you are comfortable with. Okay, so 1 is alpha degrees, 2 is beta degrees, 3 is gamma degrees, 4 is theta degrees. Now we know alpha and beta are 180 degrees. Okay, beta and gamma, they are also 180 degrees, which is equal to alpha and beta. So beta plus gamma is equal to alpha plus beta. Okay, so gamma is going to be equal to alpha plus beta minus beta, which implies that gamma is equal to alpha. Similarly, we can easily prove that beta is equal to theta. Why? Alpha plus beta is 180 degrees. Okay, theta plus alpha is also 180 degrees. So alpha plus beta is equal to theta plus alpha. So beta is equal to theta plus alpha minus alpha, which is theta. So the conclusion is alpha is equal to, the final conclusion is alpha is equal to gamma and beta is equal to theta. So we have derived this conclusion from theorem 1. That is why I call the second theorem is an offspring, a direct offspring of the first theorem. In summary, we studied the first two theorems of plane geometry. The first theorem says that when a straight line meets the internal point of another straight line, the sum of resulting adjacent angles is going to be 180 degrees. This is theorem number 1. Theorem number 2 says that when two straight lines intersect each other, the resulting vertical opposite angles are going to be equal. So alpha is going to be equal to gamma and beta is going to be equal to theta. The second theorem is a direct offspring of the first theorem. Okay, so with that I come to the conclusion of this video. In the next video we will be looking at theorem number 3, which is the most important theorem involving straight lines. Thank you for watching.